I think that's probably a motion sensor, so that after you leave after hours, if you forget to turn the lights off, they'll shut off automatically, more than likely, because of that motion sensor. Mechanical systems, when you lay out a building, the big thing that the architect is going to need to coordinate with the engineer is mechanical spaces, mechanical rooms, electrical rooms. You think those big air handlers can just put them over in a tiny little corner somewhere? No, the room itself may be an 8 by 10, it may be a 12 by 14 or whatever the air handler needs to be. Mechanical systems typically are broken up into split systems. A split system would involve an air handling unit indoors, which is the fan and the heat. The outside portion is the ACCU, or air cool condensing unit. It's the compressor and coils, cooling coils. The two are interconnected with refrigerant piping. So the closer they are together, the more efficient they work, and the less the system is going to cost for the contractor to put in. Typically, you try to keep that below 100 feet, okay? All of these systems require mechanical or electrical disconnects, so you want to get those as close to your panel board as possible to minimize the length of the feeder, the run, the wire. Another system besides a split system is a packaged unit, a rooftop unit. On some larger buildings, you got like HEB or somewhere, you got really big rooftop units which are combined. It's got both the air handler and the compressor inside. It's just one big unit, and it's really heavy. So a consideration there for an architect would be, where do you place that big 10,000-pound unit? You just set it out in the middle of a bay? No, you want to have it over some structure or close to a structure. They're set on curbs normally, and another consideration is air or a windstorm. Down in these parts of the country, you've got Corpus is rated for 120 mile an hour wind. So you have to bolt it down to the roof to withstand 120 mile an hour wind. If you're out on the island, it's 130 mile an hour wind zone rating. So even though it's condensed, it's a packaged unit, but if it's outside like that, or even on the floor, air cool condensing unit would still have to be bolted to the pad. So that's a consideration. Anything you put outside has to be windstorm approved. Anything you hang on a building, you got to make sure it's windstorm approved. That's a big thing down here. You guys probably know about that. I have seen some cinder blocks sitting on antennas on roofs, which is not windstorm approved, so I don't take pictures of that and I don't look at it. I don't pay attention to that. That's not my job anymore. I used to be a windstorm engineer. I am not anymore, thank the Lord. Electrical devices, everything you see here has got electricity. The receptacles on the wall, the lighting, air conditioning, hot water, all that requires electricity or gas for the hot water. It's not magic. That power comes from somewhere. When you're outside, you see these big green boxes on the floor, on the ground, like 6 by 6 or 6 by 8 or whatever. Those are pad-mounted transformers. They bring high voltage, like 10,000 volts down to 480 volts or 120, 208 volt into the building. And inside your building, you'll have panel boards, lined up panel boards. Those panels feed lighting, receptacles. If you bring in 277, 480, which is good for big air conditioning units and lighting at 277, then you have to further reduce that to another transformer to 120, 208 or 120, 240 to serve receptacles and that type of stuff. These receptacles are always going to be 120 volt, okay? As far as an architect, what you can do to help the engineer is to go ahead and think about, he's going to need an electrical room, or he's going to need some place to put his panels. Now, you can flush mount a panel in the wall going down a corridor and minimize the space. They typically don't need as much space as a mechanical room does. Mechanical, there's no way around it. You're either indoor unit, the air handler, you'll either have to put it in a closet or in a room or suspend it from the structure. And again, if you suspend it from the structure, make sure the structural engineer knows about that and you've worked that out with the structure, okay? Plumbing fixtures, you guys all know in the kitchen and in the restroom, you got plumbing fixtures. You got flush valves, you got tank top water closets, you got water coolers, you got water heaters. You got to think about how to get if it's a gas system, then you got to think about how to get gas to the building. If it's a commercial kitchen, then you've got a lot of gas in there typically for cooking. You've got hoods, you've got exhaust fans, kitchen supply fans, makeup air fans. in a kitchen, when you're exhausting all the hot air out from the cooking area, well, you have to bring fresh air in, but it can't be just this hot, humid Corpus Christi air. It's got to be preconditioned. So you bring that in through an air handler unit or rooftop unit that's conditioning the air. Hot air out, cool air in. So everybody's good with that. Does everybody here work with AutoCAD? Everybody here works on AutoCAD? Y'all work in 2D, plan view, or do you work in 3D? Both? Y'all are way up on me. I have never seen 3D. I would be afraid to look at 3D CAD. Everything I do is 2D. So y'all are ahead of me on that. I have to visually look at it, but then when I'm routing ductwork, above the ceiling there's a system of ductwork for all these supply diffusers and return diffusers. Well, that ductwork's not flat, it's got depth. So you have to account for the space above the ceiling to get that ductwork routed. Well, if you're working in 3D CAD already, then you're going to be able to rotate it up and look at an elevation, or maybe a isometric view, which is going to be a big help. That's way better than I learned it. One of these days, I've been doing this for 20 years, I might start 3D next year. I probably won't. I'm probably just old school enough, I'll stay with the 2D. I'm good with flat. It looks good. I can tell if I'm dealing, and I deal with a lot of architects, I tell them I need an elevation, they roll it up, and I say, oh yeah, that's how they work. Okay, I have this much room. Another time that you really want to pay attention to elevations is mounting heights of devices. The switches code tells you a certain range of heights to put that switch. Same with receptacles, same with fire alarm devices. Fire alarm device is very specific. The manual pull station, the strobe horn, the visual device in the restroom, those things have very specific mounting heights, so you want to kind of pay attention to that. Those will all help you out with dealing with an engineer. Any questions on just brief MEP so far?
I've got a question.
Okay.
We were in another class that he's in, we were talking about how many of these, is there a rule of thumb for registers per square foot?
A good rule of thumb is 1 ton per 300 square feet, 300 to 500 square feet, 1 ton of air conditioning. That's a good rule of thumb. Now, these deliver a CFM, a cubic foot per minute of pressure of airflow through that device. Your unit is going to deliver a large amount of air, a large CFM amount. It's under a lot of pressure, but it disperses out among these. So you want to consider sound. You don't want to hear this, and this is well designed. Somebody did this well. You don't hear it, or you don't hear it much. If you reduce the number of these, the air will still get in here, but you're going to hear a blowing sound. Okay. So you not only want to evenly distribute it, but you want to also minimize the sound. And that's the big thing. Experience will come with, you can look at these devices. These are probably about every 8 by 10, about every 80 square feet or so. Probably on center 8 by 10 or maybe every 100 square feet. You have a device, 10 by 10. But there's no rule of, I'm not a mechanic, I need Daniel here. I asked him to come and he wouldn't come. So I said, I got it, all right.
Well, we're just rule of thumb people, so that's.
Right. 300 square feet per ton, unless it's like a very open area with no restrictions and very few occupants, then you can go probably 500 square feet per ton. That's a pretty good rule of thumb.
Okay.
Okay. A little bit more into the HVAC side. HVAC is heating, ventilating, and air conditioning. That's what a mechanical engineer does most of the time. He actually breaks it up into HVAC and plumbing, but a big portion of his job is to look at HVAC. And like I said before, they need room for their devices. Outside, it's no big deal. If it's a rooftop unit, you just find structure to put it over and you're good. Out on the ground, it's no big deal. You just avoid conflicts with a walkway or a sidewalk or planters. You want to try and keep them to the side or to the back as much as possible. Indoors, the air handling unit is the big issue because some of those, the one in this building is massive. It's going to be a massive air handler. So there's a room down probably in the basement. You walk in there and it looks like a submarine. It's just wall-to-wall machines. So that is a consideration to always think about the weight and dimensions of these devices, especially the air handler. talked about that. Okay. By code, any space you're in that's occupied is required to be heated and ventilated. It is not required to be air conditioned. But down here in Corpus Christi, we're gonna be air conditioned. I'll tell you that, I'm not gonna work anywhere where it's not air conditioned. Inside. But if you say have a big warehouse and it's occupied, then it has to be heated and ventilated. It does not have to be air conditioned. The heating and ventilation is accomplished through typically either gas or electric unit heaters, forced air blowing out into the space. And we look at, one of the reasons it's heated is to avoid pipes freezing, especially sprinkler piping. If you have a sprinkler room with a standpipe coming up, 6 or 8 inch or 12-inch standpipe, then you'll have a unit heater within that room also to keep that pipe from freezing. And it will maintain just above freezing for that, whatever it takes. But in an occupied space, we normally don't let it get below 68 degrees, or try and maintain it at 68 degrees, even in the wintertime. To ventilate it, you will probably have a large wall-mounted exhaust fan in one wall up high, and then a louver, an intake louver, across the space diagonally low so that you pull air across the entire space. The louver is nothing more than an intake. It's going to have a grill, probably to keep birds and insects out, at least birds and rodents. But the louver blades, either they could be fixed or they could be movable. If they're movable, then they can either be gravity or electric. Gravity is just, with no airflow, it's shut. When the exhaust fan turns on, it opens up because it's pulling air through there. Electrical, if it's a motorized damper, then obviously you're going to have to coordinate with the electrical and get power to it. But from a architectural standpoint, you have to think about that's a really big fan up there, and that's a really large opening over there. It may be a 6 by 6, it may be an 8 by 8. Well, if you have, say, a metal building, then you have to account for the way the girders are set, the purlins up high, and then the structure itself. You have to make blockouts for that. The metal building guy would have to know that. If you're designing that building, you need to know there's a big 8 foot by 8 foot space over here that has to have a louver. There may be multiple louvers. We did a 100,000 square foot building out in Eagle Pass, and it had a lot of louvers and a lot of fans. I'll get back to this a little bit. When you're looking at, now your mechanical engineer will take care of this, but he's going to need to coordinate with you, the architect. Above the ceiling is a critical place for ductwork. These ducts are typically 14 feet high, or 14 inches high by 10 inches wide, and above the ceiling is not empty by any means. It has all kinds of stuff up there. If these lights were recessed, say they were can lights or down lights, they would stick up above the ceiling maybe 6 or 8 inches. So you have to avoid the lighting to get your ductwork through. If it's out in the corridor, you want your lighting centered down the corridor. So you don't want the ductwork also running down the center of the corridor. Move the ductwork one way or the other, because lighting rules. You can move the ductwork, but the lighting has got to be there because it's serving a function. This is ducted return, I would think. So there is actually a trunk line going back to the unit. If it did not have that duct, then this would be a return air plenum above the space. All that space up there would be a return air space, which you need to know about it in your planning, because in a return air plenum, you cannot have PVC piping there. It's a fire hazard, and if that catches on fire in a return air plenum, you're breathing toxic smoke. So that's a problem. Any low voltage wiring or cabling that you put up there would have to be plenum rated so that it does not produce a toxic smoke if it catches on fire. So that's just another thing to keep in mind. A lot of this the engineer takes care of, and it's automatic, but if you don't have a good engineer, he may forget it, and then we're all in this together. If your plans are connected to his plans, all of a sudden they're asking you, the architect, why'd you let that happen? Well, I should have got a good engineer to start with that knows about all this stuff. So we catch stuff that y'all miss, y'all catch stuff that we miss, so it's all together. You know that obviously electrical is connected to both plumbing and HVAC, because plumbing fixture or electric water heaters have to have power. All the units that are HVAC